This is the final section of 10-1, and we'll be looking at amplifier configurations. Three common ways a transistor may be configured as an amplifier include common emitter amplifier, common collector, or as it's often referred to, a emitter follower amplifier, and a common base amplifier. The common emitter is probably by far the most common. Okay, here we have the common emitter amplifier. Now, the reason that it's called a common emitter amplifier is that for purposes of AC, the emitter is the point where the AC signal goes to ground, hence the term common, meaning ground. The emitter is the ground for AC, and so the signal source here is our AC signal source that comes in, and then the ground is actually through this capacitor. Remember that a capacitor is a ground for AC and an open for DC. So signal source goes in like this, and since the AC is grounded through the emitter, hence we have the term common emitter. Okay, so here we have the basic configuration. We have, first of all, I've got some things to note here. Biasing resistors R1 and R2 form a voltage divider. If we had, and I'm just going to throw some values in here, if we had 10 volts here, and we had, I'm not going to specify that, let's just pretend we had a voltage divider here, and we had 2.7 volts DC at this point. Coming over here to the emitter, we would have a 0.7 drop, so that would put about 2 volts here, and these are all DC values, by the way. This 2 volts would be across R4. That would cause a current to flow. That current would go through to the collector, and it would drop a voltage across R3, and part of that, and so we'd have a voltage drop here, and let's just pretend that we have 5 volts on the collector right here. So these two are setting the biasing for the base, and then R4 and R3 would establish the values that you would see at the emitter and the collector. Well, really the collector, because the voltage here on the base actually determines what the emitter voltage will be here, because there's going to be a 0.7 drop right here. So at this point, let's see, we have coupling caps. So let's see, we have 3 capacitors in this circuit. We already talked about this one. This one provides for the AC ground. This one, notice we have DC felt right here. If we did not have this cap here, then the DC would pass over to our signal source. We don't want that, but we do want to be able to pass the AC signal into the base of our transistor. So this is a coupling cap here. This is also a coupling capacitor. Notice that if we were to look on an oscilloscope and we were to look at this point right here, we would see 5 volts DC when there's no signal at all here. Now when we import a signal, we send a signal source in, then we will have an output here. Now the thing is that the output will be riding at a 5 volt DC level. So this is where we'll have AC riding at a DC level. And the reason that I chose 5 volts here is that represents what we call an operating point. Sometimes they call it the quiescent operating point. The reason for this is that this value allows for the maximum signal change. Now notice here we have 5. If they have 5 volts, notice the signal, the power supply is 10 volts, so the signal could, I mean, realistically it can't go that high, but at least in theory we could say, well, it could go up to 10 volts and it could go down as low as 0, because those are the 2 reference points here, 0 and 10 volts. So this would optimize the passage of signal. Now when you get into the real analysis, you'll find that we would not be able to go to 10 or to 0, but placing the operating point in the middle gives us, the ability to get the most signal swing as possible. So this represents a common emitter amplifier. I don't expect you to know these DC values. Your text doesn't go into it, and I'm going to be doing a more thorough analysis on a presentation. It won't be a required one, but I just do want to show you a more thorough analysis. In fact, the circuit I'll be doing that on is this one. I'm going to go through and calculate all the DC values, and then we'll calculate all the AC values, and then we'll make, based on the AC and DC calculations, we will send in an input signal, and we will estimate what will the output be. And again, this is not required material. Your text does not go into this. This is just something extra just for your interest. Okay, then the next one here, this is called a common collector, and this is often referred to as an emitter follower. And again, the term common collector means that for AC purposes, the collector represents a path to ground. Now, this amplifier is a little bit different than what you might think. Notice here it says emitter follower. So you come in here with an input, and the output actually comes off the emitter. Okay. This particular circuit, the gain, we calculate gain to be 1. So you say, well, what in the world are we doing with this? There's no gain. I mean, it's an amplifier that does not, I don't see any amplification here. Well, what we have here is a circuit that is suitable for driving low impedance loads. Remember we said that with a signal source or an amplifier, we want to have low output impedance. Well, when we take a signal off of the emitter, it steps the impedance down significantly. So this is one way to have a output impedance that is very low, is to take the output off of the emitter. So what would happen is that in stages previous to this, we would amplify the signal to the signal size that we want, and then in the final stage we would send it through this emitter follower, and it wouldn't give us any gain, but it would lower the output impedance so we could have maximum transfer of signal to the next stage. Now let's see, I've got some notes here. DC bias, so we have R2, the emitter, and the R1 here. This would establish the DC levels for biasing. The coupling would be across C1. The input would, the input value would come down here across R2, and then the value felt across R2 would be sent over here out as our output. C2 is a decoupling capacitor, which places the collector at AC ground. The output looks like the input, both size and shape, and there is no phase inversion here as well. Okay, the last one we're going to look at is a common base amplifier. In some respects, it looks kind of like the common emitter. We have the biasing with R1 and R2 to establish the voltage at the base, and then we'd have the 0.7 drop here, which would make a current across, or a voltage across R3, and then that would give us the current through R4, and again we'd have our coupling capacitor here. The main difference between this and the common emitter is that in this case, rather than using the base for the input, we're going to use the emitter for the input, and the base will be the common ground. This is not a common configuration. The common emitter is much more common, but theory is basically the same. We develop a voltage here, it's felt across the emitter, which is passed to the collector, and then we have amplification. Let's see, what do I say? Voltage is felt across the base emitter junction, developing a current that is passed to the collector. The current is felt across the parallel values of R4 and R3. Okay, this value comes in, it has two paths through R3 or R4, and establishes an output voltage. Okay, summary of bipolar transistors. The base of the transistor is thin and lightly doped, so we talked about this many times, NPN, so that if this NPN, the base would be the P material, be very thin and lightly doped. The emitter is heavily doped. The collector is moderately doped. The sum of the base and collector currents is equal to the emitter current, and we looked at that. We had we had our transistor. I didn't draw this real good, but here we go. Okay, so all current comes up through the emitter. It either goes to the collector or goes to the base. And remember that probably 95% goes this way. In fact, it's 95 to 99%. But at any rate, the sum of the emitter current will be equal to the currents going through the base and the collector. Base current is typically less than 5% of the emitter current. Cutoff is where there is no substantial transistor current. Saturation is a condition where the transistor is conducting maximum current. Saturation and cutoff represent the two extremes of transistor behavior, and these are what was used in digital circuits. Between saturation and cutoff lies the linear region of the transistor, and this is where we would have amplification. The quiescent operating point is established by DC biasing, and there are many ways to bias a transistor, and we looked at 3 of them in this section quite briefly.